Thank you, Seda, for the nice introduction, and good morning, everyone, and thanks for coming to my talk. It's a great pleasure for me to be here and have the opportunity to share my research and my work during my PhD and postdoc with you. So as Seda mentioned, my PhD and postdoc research has been mainly focused on integrated circuit designs with a variety of applications ranging from high-speed optical and electrical interconnects for chip-to-chip and on-chip communication to biomedical implant systems and sensory microarrays. So for the interest of time, I'm not going to be able to go over all these topics. So what I've chosen to present today is the chip-to-chip optical interconnects as well as on-chip electrical interconnects. And then in the second part of my talk, I'll be presenting to you medical implantable system with the main focus on continuous glucose monitoring. So I have also done some work on retinal implants, which I'm not going to cover, but there are some publications that if you're interested, you can refer to and learn more about it. So, so I will start my talk with an overview of my work, and I'll move on to optical and electrical interconnects for high-speed communication. In the second part of my talk, as I mentioned, I will talk about implantable medical devices, and I will conclude my talk with my future research directions. So as you all know, over the past few decades, the processing capability has scaled tremendously, and nowadays we have processors that are able to do a huge amount of processing owing to the famous Moore's law that tells us or predicts that the number of transistors on a CMOS chip almost doubles every 2 years. And basically that has been the main drive force for the semiconductor industry so far, and big companies like Intel and IBM and TSMC are trying to comply with this roadmap that Gordon Moore has laid down about 50 or 60 years ago. So if we go back and look at the processor history, at the early ages of the processor designs, the improvement in processing capability was achieved through increasing the number of transistors on a chip as well as increasing the clock frequency, until we reached a point that increasing the clock frequency was giving better processing capability at the cost of excessive power consumption. So a paradigm change happened, and multi-core processors came into existence to do more efficient, to get better performance, as well as with less power consumption. And nowadays we have processors with tens of cores that are able to do tera and tera scale computing, and soon enough we will be having processors with hundreds of cores that are capable of doing exascale computing. And all these computation capability and all this data that is processed in a processor needs to be communicated between the cores as well as with the outside world. So this increase in computing capability also requires a corresponding increase in the the bandwidth of communication between cores as well as from a processor to other processors and other devices. So as an example, you can see here a supercomputer from IBM that is capable of doing tera and exascale and petascale computing. So if we look at the hierarchy of processing, we will see that it starts with a compute chip that has multiple cores that are interconnected through copper wires, and then compute cards, and so on and so forth up to the system level that we are having here. And all these units needs to be communicating to each other. And as the processing capability increases, the bandwidth of this communication also needs to be increased. So the natural way of communication is doing it using copper wires through electrical signals. But the problem with copper wires is that their bandwidth is limited. And that limited bandwidth is mainly due to the frequency-dependent loss that will cause intersymbol interference. And this intersymbol interference is caused because of the pulse dispersion that the limited bandwidth of the channel will impose. And also the other problem will be electromagnetic coupling that will create noise, crosstalk noise. And therefore we will need sophisticated equalization circuitry to tackle this problem. And at some point this circuitry, this equalization circuitry is going to become very power hungry, and it makes scaling in the bandwidth hard within a reasonable power budget. So an alternative to electrical interconnects is optical signaling. So optical signaling is very appealing because of numerous reasons. So optical medium, optical fibers are very low loss. They provide a very high bandwidth. It makes it possible to do wavelength division multiplexing to increase the aggregate data rate, and basically using parallelism to increase the aggregate data rate. And also it provides very high propagation speed, near the speed of light propagation. So this optical signaling is very promising, but we need to also keep in mind that the reason we are not any more interested in copper interconnects is because of the excessive power consumption that they will impose on the system. So in order for optical interconnects to become a viable solution, we have to have very low power electronics so that it will provide a better solution than the copper interconnects. So, in the first part of my talk, I will go over the optical system that I have been working during my PhD. So an instrumental part of an optical communication system is an optical receiver, and the role of an optical receiver is to basically convert the optical. The optical receiver is composed of a photodiode and a readout circuitry. So the role of the photodiode is to convert the optical received signal to an electrical current, and the readout circuitry will convert this current into a voltage and makes it ready for data resolution. So the simplest way to do this, so basically an optical receiver from a circuit point of view should, the way it acts is to convert this optically generated current into a voltage and the data resolution. So the simplest way to do this is to use a simple resistor to convert this optically generated current into a voltage, and then using some amplification to perform the data resolution. But the problem with this approach is that it will create a trade-off between bandwidth and the sensitivity. So basically, in order to get a good sensitivity, we tend to increase the resistance of the size of this resistor, which on the other hand will lowers the bandwidth at the input node and basically limits the data rate. So So therefore, it will create this trade-off between sensitivity and data rate. And it will be only maybe an interesting solution if we have a very small parasitic capacitance from the photodiode. So in order to break this trade-off between sensitivity and bandwidth, designers use transimpedance amplifier, which uses feedback to create a low impedance at the input node, and at the same time provides a high transimpedance gain using this amplifier in feedback. The problem with TIA is that it requires a high gain bandwidth product, especially if we are trying to achieve high data rates, and high gain bandwidth products translates into high power and in some cases high large area, silicon area. And therefore it's not a very interesting solution for highly parallel links in which we are limited with our overall power. So an alternative to TIAs is to use an integrating front end. So in an integrating front end, what we basically do is to integrate the optically generated current from the photodiode on a capacitor. And basically, a received 1 and a received 0 will create a distinct voltage that can be used to resolve the received signal. The problem here is that, as you can see, over time, receiving 1s and 0s, this voltage at this node will monotonically increase, and at some point we will hit a saturation level. So in order to resolve that, we can basically subtract a DC current from the photodiode current, and therefore make our voltage bipolar and basically DC balanced. But still, you can see that if we receive long sequences of 1s and 0s, we are still prone to saturation. So that's something that needs to be kept in mind. And then we can use this so-called technique of double sampling and resolve the received signal by basically sampling this voltage at the beginning and end of each bit interval, and then if the sample is larger than the previous one, we can we know that we have received the 1, and if the sample at the end of the bit interval is smaller than the other sample, we can know that we have received a 0. So far everything is good. This is a very nice technique. It actually employs mainly digital blocks, so it makes it very suitable for for advanced technologies. It's going to be very good for scaling. It doesn't need any high gain stages that operate at the high data rate, at the high speed, and also it performs inherent single-ended to differential conversion at the front end. And also, the other nice thing about this technique is that it makes demultiplexing possible at the front end. So basically, we immediately at the front end, we are reducing our data rate by a factor of 2 or 4, depending on the number of samplers that we have at the input. So, but the main problem of this technique is that, as I mentioned, we need to have some sort of encoding to ensure that there is no long sequences of 1s or 0s in our received signal. So now let's revisit the RC front end that I mentioned in the very beginning. Now, if we choose our our resistor, our front end resistor, large, so that our bit interval is much smaller than the time constant at the input, we are basically we will basically end up with such a voltage. For example, if we receive a long sequence of 1s, and you can see here that we have already resolved the saturation problem because of adding this resistor. So basically what will happen is that our output voltage will saturate at a level much smaller than our saturation limit, and therefore we have solved the problem of using any encoding technique. But then we can use the same double sampling technique to resolve our received signal. So basically, by sampling this voltage at the input, we can basically resolve our received signal. The problem here is that as the time progresses and we receive, say, many ones, our double sampled voltage, so I will call this difference between the two samples the double sample voltage. So this double sample voltage will exponentially decay to 0. And at some point we will be below the noise level, and therefore it will be impossible to resolve a received bit if we are receiving a long sequence of ones or zeros. In order to resolve this problem, what we have proposed to do is to use a technique called dynamic offset modulation. So basically the way this technique works is that depending on the voltage at this node, we dynamically change the offset of the next stage comparator. And basically by doing that, we will end up having, instead of an exponentially decaying double sampled voltage, we will be having a constant double sampled voltage, and therefore we will be able to resolve our received signal without any error. So this is actually qualitatively explaining this technique. So now let's look a little bit deeper into this technique and do some analysis. So the way a double sampling system works is basically explained in this block diagram. So basically the previous sample is subtracted from the current sample, and we will end up with the double sampling voltage, and then we will use a comparator to decide whether we have if we have a positive or negative double sample voltage, and we will decide whether if we have received a 1 or 0. Now, if we also include the offset, the dynamic offset modulation, so basically the way the offset dynamic modulation works is that depending on the previous sampled signal, we will subtract or add some voltage from our old double sampled signal, and we'll come up with we will end up with a new double sampled voltage, which we call delta V prime n. And this delta V prime n, we can show that if we choose beta equal to this quantity, this double sample voltage will be basically independent of time, and therefore we will be having a constant double sample voltage irrespective of the received input sequence. So we designed we implemented this technique in 65 nanometer CMOS technology and used optical and electrical measurement setups to characterize its functionality. So in order to characterize its optical functionality, we hybrid integrated a photodiode to the CMOS chip and connected it with wire bonds, and used single mode fiber to couple light into the photodiode. And this actually shows the optical measurement setup. So using this technique, we were able to achieve up to 24 gigabit per second of optical data rate with a reasonable optical sensitivity. So this graph actually shows the electrical measurement of the system. So basically, for electrical measurements, we did not use a photodiode. We basically emulated the effect of a photodiode by a current source on chip. But then we didn't stop there. We moved forward and used photodiode, as I showed in the previous slide, and measured the functionality of the system. And as you can see, in optical measurement setup, we could also achieve up to 24 gigabit per second at almost minus 5 dBm of optical sensitivity. And it should be also noted that in this graph, the loss due to the coupling was not considered. So we actually expect to have about 4 to 5 dB of loss due to the coupling from the single mode fiber to the photodiode. And if you look at the power numbers, as I mentioned, because we are mainly using digital blocks, the power almost linearly increases with the data rate, which is expected from mainly digital system, and the power consumption per gigabit per second is almost constant, which is also expected from such a system. So, next I'm going to talk about on-chip interconnects. So as I mentioned earlier, nowadays we have processors with many cores, and these cores need to be communicating with each other. And in order to have high processing capability, these on-chip interconnects need to have low latency, and we need to have very efficient communication between the chips because of the limited power budget that we have for communication. So if we look at on-chip interconnects, we'll see that as technology scales, the cross-sectional area of on-chip interconnects, which are mainly made of copper, are becoming smaller and smaller. And that means that our on-chip interconnects are becoming more and more RC limited. And we know that RC limited interconnects have delays proportional to their square length. And as the chips become larger and the cores are more distant from each other, this latency becomes much bigger. And as the technology scales, because the cross-sectional area becomes smaller and smaller, the size of these resistors becomes larger and larger. The capacitors remain almost constant because all the dimensions are shrinked at the same time, but the resistance gets smaller and smaller. So as the technology scales, we expect the delays to become larger and larger, and that's kind of shown in this graph. So the way designers have been tackling this problem has been to use repeaters. Basically, by inserting repeaters and basically breaking the line into segments and inserting the repeaters, we can basically reduce this delay relation with the length to a proportional relation, as opposed to proportional to a square of the distance. But this actually comes at a cost of more power consumption due to these repeaters, and also costs us real estate in silicon. And as you can see, inserting repeaters is going to help with the delay, but as I mentioned, it comes at the cost of energy. And as you can see here, as the technology scales, the number of repeaters that we need to use becomes larger and larger, and therefore the power associated with it grows almost exponentially. And as you can see here, interconnection power is a major portion of the power consumption in a processor. Of course, this is for a single core processor. Using multi-core processors, this becomes less, but anyhow, the power associated with interconnects is a major portion of the processor power. So we need to find a way to reduce this power consumption, basically. So what we actually have proposed to do is to basically use a similar technique to what we used for our optical signal. So, so basically in this technique, at the transmitter side, we use simple inverters, and by adding a capacitor between the driver, the line driver, and the interconnect, we basically create some pre-emphasis at the receiver, pre-emphasis to the signal, so that so that the limited bandwidth of this interconnect can be somehow compensated for. And adding this capacitor also helps reducing the signal swing on the interconnect, which is mainly capacitive. And you know from digital design that a capacitive load, the power associated with a capacitive load when it's switching is basically proportional to square of its signal swing. So if we can somehow reduce this signal swing, we are basically reducing our power quite drastically. So basically, addition of this capacitor both helps with pre-emphasizing the signal and reducing the power consumption of the driver. And at the receiver side, because we are our interconnects is mainly RC limited, we are basically dealing with exponential signals. And as Elmore delay approximation tells us, we are basically dealing with a system with a dominant pole. So we are basically dealing with a first order system, and therefore we are dealing with exponential signals. So we can use the exact same technique that we use for optical signaling. So the double sampling technique, we can employ the double sampling technique to basically resolve whether we have received a 1 and 0. And here we actually have used a demultiplexing factor of 4, so that the output data rate is reduced by a factor of 4, and therefore we have also done some demultiplexing right at the receiver.
Question?
Sure.
In that circuit, why is the bias voltage VDD set to be VDD at the termination?
Here?
Why isn't something between VDD and VSS?
Basically, having VDD at this point will help the next state sample and hold. For the sample and hold, we are using a switch.
Oh, I see. So you want voltages over VDD for the because when you bias it at VDD,
right,
the transitions are going to take you above and below VDD.
Right, but because it's low swing, it's going to be a little bit higher than VDD. So it's not going to stress our system. So we are not going to be worried about reliability issues. But then the way it helps is that because the next stage sample and hold uses a transistor switch, and we are using PMOS transistors, it's good to have VDD so that our switch turns on and off completely. So, we implemented this technique in 28 nanometer CMOS technology, and we use this technique for channels with different lengths. These are typical lengths for chip-to-chip communication, 5, 7 to 10 millimeter, and we actually could achieve up to 20 gigabit per second of data rate with less than 0.2 picojoule per bit of power efficiency. So one thing that needs to be noted is that because we are using single-ended signaling, we need to be also careful about crosstalk between different channels. So what we have done to compensate for it is to use ground shields between different channels. So what we have done is to insert ground shields between adjacent channels so that we minimize the amount of crosstalk between the two channels. And as you can see here, the power consumption is almost linearly increasing, and that's mainly due to the fact that this is using mainly digital blocks. And this is actually very favorable for digital designers because they tend to go to more and more advanced technologies, and they like to have blocks that are easily portable to new technologies. So using mainly digital techniques is going to help them to facilitate this process, facilitate the migration process to newer technologies.
With the interdigitated grounds,
Mhm.
you really have a transmission line structure, don't you?
Pre-
Can you characterize it as a transmission line?
It can be considered as a transmission line, but with a very basically it's a very lossy transmission line because it's highly resistive. So it's not like a lossless transmission line with 50 ohm characteristic impedance. So its impedance, its characteristic impedance is much different, and also as I showed here, so basically it has a huge amount of loss at DC, which is due to its resistance, and then due to its RC nature, it has a large amount of frequency-dependent insertion loss. Yeah, but
One more question. The sample and hold that's at the termination now.
sure.
Does that actually, when you sample, does it actually induce an artifact back in the line?
Because we are using a very small feature size technology, the transistors are pretty small. So it would maybe introduce some kickbacks to the line, but it's kind of negligible because we also have this termination resistor that sets the voltage here. So it's not that noticeable. So we didn't see much of effect in our measurements basically from that.
Thank you.
Simulation, both simulation and measurements. So so as I mentioned, we use ground shield to reduce crosstalk, and that actually helped a lot. Basically, having an aggressor signal from the adjacent line only decreased our signal integrity by about 5% due to using this ground shielding. So compared to other designs, this design offers one of the highest data rates at the lowest, almost best energy efficiency, and at the same time, the one thing that is very important for on-chip interconnects is bandwidth density. So basically, because our real estate is limited, we want to have as high as bandwidth density as possible. So basically, this technique, we have used minimum feature size copper traces, and therefore we could achieve the highest bandwidth density that has been reported in the literature. So that brings me to the second part of my talk, which is on implantable systems, medical devices, with the focus on glucose monitoring, continuous glucose monitoring. So as you can see, over time, the healthcare spending has grown quite drastically, and it has not been proportional to any other to the rest of economy over the last few decades, and this is mainly due to hospitalization and doctor's visit. So in order to reduce this burden of healthcare expenses, it's very desirable to have closed loop systems that can monitor monitor patients and basically bring the point of care from hospitals and doctors' office into the patient's side. So basically, this way we can monitor patients, have some feedback systems, some closed loop systems to maybe do some diagnosis, to do maybe some sort of treatments, and if things become worse, we can be connected through a secure network to the healthcare providers. So to emergency, to doctor or to hospitals. So basically, this kind of technology can greatly help reduce the healthcare costs. And as you might know, 20% of US GDP is nowadays spent on healthcare. So that's actually a huge number, and it will be very beneficial if we can reduce that cost. So as an example, I will be mainly focused on diabetics. So this chart basically shows the number of diabetic people in different regions of the world in 2000 and the prediction of the number of diabetic people in 2013 and 30. And as you can see, the population of diabetic people is growing quite drastically, and it's already pretty high. These numbers are in million. So it actually has a huge economical burden, as well as these kind of patients are in a huge amount of pain, and it will be great if we can find a way to help their quality of life by using new technologies. So so the way diabetic people manage their disease nowadays is to basically measure their blood glucose using by pricking their finger a few times a day, and using these kind of devices to measure their blood glucose, and then decide whether if he or she wants to have the muffin, or if he needs to, say, inject some insulin. So this process is accurate, but it's not continuous, and it's kind of painful for the patients because they need to do the pricking multiple times in a day. And of course, it's not. It doesn't provide a continuous measurements. So as you can see, the blood, the glucose level in blood changes quite often during the day, and after any meal, long time after a meal, the blood glucose drops. So basically, it's very suitable if we can do some sort of continuous glucose monitoring to find the trends, and therefore remove the need for pricking the finger every now and then and find out what the blood glucose level is. So there are some minimally invasive techniques to proposed techniques to do that, like some wearable devices using flexible circuits, but that try to get glucose level from body sweat, which are not very accurate. There is also ways to do it with spectroscopy, say Raman spectroscopy, but that's also very prone to artifacts like motion. It's not a reliable way of measuring blood glucose. So there are other techniques to do glucose measurements. They're more invasive, but they will provide continuous glucose monitoring. So some of these devices are shown here. They basically measure glucose from interstitial fluid. So basically, there is a little bit of delay between blood glucose concentration and interstitial fluid glucose concentration, and that's mainly due to the fact that there is a diffusion delay between the blood and the interstitial fluid. But nevertheless, it's providing valuable information because it's giving the trend of glucose concentration change. But because it uses wires, it basically is implanted transcutaneously. So basically, a needle will be inserted through the skin and goes to the interstitial, into the subcutaneous area, and does the glucose measurement. There are also devices that are fully implantable and use wireless technology to communicate with the outside world, but as you can see, the size is quite big and they are not very practical for implantation. So what we are trying to do here is to come up with an implantable system that. So the other thing I needed to mention here is that because these devices are transcutaneous and they have wires, they are very prone. They will cause irritation and inflammation, and they are not recommended to be worn for more than a week or two. So the lifetime is also short for these kind of sensors. Even though this is the fact that it seems to be invasive, but the diabetic people are very willing to have this kind of device so that they can have their glucose concentration trend and not have to prick their fingers every now and then during the day. So if we can come up with a device that can last for a few weeks and does accurate glucose measurements, that will be a very good news for these kind of patients. So what we are basically looking into is to come up with a device that could be fully implanted and provides information for more than a few weeks and have minimal harm to the body. So when a sensor is implanted, so the body will react to it. So anything that is implanted will experience foreign body response. And the foreign body response, the way it works is that it will gradually encapsulate the device. And therefore, it tries to basically starve the foreign body that is inserted into the body. So basically, it will encapsulate the device so that there will be no flux of nutrients to the sensor, and basically that's what we are trying to measure. So we are trying to measure glucose. So if encapsulation happens, we are basically getting less and less signals, and at some point we will lose our signal. So research has shown that by making the device smaller and smaller, the foreign body response will reduce drastically, and this encapsulation layer will become thinner and thinner. And the thinner the encapsulation layer is, the more diffusion we will get and less latency we will be having from the blood glucose concentration. So basically, the lesson learned was that we need to have very small devices that will minimize the body response. So basically, a small device also can be injected instead of being implanted using incision. So it will also make the implantation process easier and less painful. Also, as I mentioned, it will reduce the body response. We can also be able to do localized sensing. Of course, cost will be reduced, and toxicity level is reduced. So basically, we will be using some chemicals to do the sensing. And if the device is already small, the amount of chemicals will be smaller, will become small, and will be below the toxicity level. So that's also another beauty of having a tiny, small device. So in that sense, that kind of device is not going to be a good candidate. And what we are trying to do is basically to make a fully integrated device on a CMOS platform so that we can do blood glucose monitoring and also being able to communicate with the outside world to provide the patient with the with the blood glucose readings. So the state of the art, most of you might have heard about the new cool device from Google that uses a contact lens to measure glucose concentration in the tear. So this device is very cool, but the thing here is that there's no good evidence that the tear glucose level has a good correlation with blood glucose level. So that's the main problem with this device. And also, if there is a correlation, we don't know how much of the latency we should expect from blood to tear. So basically, interstitial fluid is almost in direct contact with arteries, and you will get almost immediate change in interstitial fluid glucose concentration if the blood glucose concentration changes. But in tear, it's and as a matter of fact, for a good while, people had been looking into tear glucose measurement to help with diabetic people, but this did not catch up. But now they have a better device. I'm hoping that this is going to help people with diabetes. So there are also some other devices developed by researchers that do not use a battery. Basically, they use RF powering in order to power the device. But as you can see, the device size is quite large, and it will get a huge amount of body response. And there is also some other devices, but because of this, and they are all aimed to be implantable to read from interstitial fluid, but the large size of the device will make it difficult to do the task. So, so now, in order to be able to do an implantable system that does glucose monitoring, we have to have a system that does first glucose sensing. Then we need to so this sensor will transduce the chemical signal into an electrical signal. This electrical signal needs to be processed. Also, we need to be able to somehow power the device. And then lastly, but also very importantly, we need to do the communication with the outside world to inform the patient from its glucose level. So this is how a system, an implantable glucose system, continuous glucose monitoring system would look like. So for sensing, human body is like an electrochemical machine. So we can basically use electrochemical methods to do the glucose measurements. So, and basically that's the way that the current glucose sensors are using. They basically use electrochemistry to do glucose measurements. So we have also chosen to use the same technique to do glucose measurement. For processing, CMOS has provided a good capability of processing. So that's not a big issue. The other issue is how to power the device. So this is actually a pacemaker from Medtronic. It uses a small battery, but then we would like to avoid having batteries due to their compatibility issues and also reliability issues. So we would like to, as much as possible, avoid using batteries. So let me move on and talk a little bit more about how electrochemical detection is done. So basically, electrochemical detection is done by applying a certain voltage across two electrodes. And if we have an electrochemically active agent, the electrochemically active agent will undergo a reduction or oxidation reaction. We call it redox. And this reaction would involve some electron transfer between the electrode and the substance that we are trying to measure. And this electron transfer will translate into a current. And that current is proportional to the concentration of the substance that we are looking into. So the device that does this task is called potentiostat. It basically maintains a constant voltage between the two electrodes and at the same time reads the resulting current. So this is the simplest case of an electrochemical sensor. It uses two electrodes, but then in order to improve the performance, it's desirable to add a third electrode, usually called the counter electrode, in order to maintain a constant voltage between the working and reference electrode. So basically here, the reference electrode just sets the voltage and the current is provided by these counter electrodes. In the previous case, this electrode was both setting the voltage and providing current. So if the current is large, then the voltage applied to the electrochemical active agent is not going to be well defined. But using a third electrode, we can make sure that a constant voltage is applied between the two working and reference electrodes. And that's how an electrode, an electrolyte interface is modeled. It is modeled as a double layer capacitor. So the double layer capacitor is formed between the electrode and the electrolyte. There is this Faraday resistance, which represents the amount of reaction that happens. So the reaction would involve some electron transfer or some current. So basically, we are applying a voltage and we are getting some current. So that basically translates into a resistor. And also, we will have solution resistance.
So in this circuit, then, the current flowing through what you call the RE is zero. That's what you're trying to accomplish?
Yes, exactly. So if we only have two electrodes, then the current will be flowing through REs, and because of all these resistances, the actual voltage applied to the substance is not going to be what we were intending to. So basically here, because there is no current passing through the reference electrodes, we are actually applying set voltage to our substance. So there are different electrochemical sensing methods. The simplest one is just by applying a constant voltage between the working and reference electrode. And in this case, the change in the concentration will lead into a change into current, basically the current that we are measuring. The other sensing technique, electrochemical sensing technique, is called cyclic voltammetry. We basically apply a cyclic signal, and then we will end up with a cyclic voltagram. And change in chemical concentration will lead into shift into this voltagram. And basically, we can see the change into the concentration by seeing the shift into this voltammogram. The other electrochemical sensing technique is called impedance spectroscopy. It's mainly used for affinity-based sensors in which there will be some binding process between a target and a probe and a target that will change the surface chemistry, and therefore it will change the impedance, basically the impedance between the electrodes. And we will apply a sinusoidal voltage, and then we will look at the impedance, basically the real and imaginary part of the impedance between the electrodes, and basically the change in the concentration will lead into the shift of this impedance diagram. So the way glucose is electrochemically sensed is basically shown simply here. So when we have a when we have a glucose, so basically glucose by itself inherently is not an electrochemically active substance. So we cannot directly measure it using electrochemistry. So what we need to do then, we need to functionalize our electrode with some enzyme. And the enzyme in conjunction with glucose will generate some electrochemically active substance. And that basically we use to basically measure the concentration of glucose. So this is pretty much an indirect way of measuring glucose. So the enzyme, there are different enzymes that are used for glucose measurements. The most common one is glucose oxidase. So the glucose oxidase is usually usually immobilized using hydrogel, using BSA and some other chemicals to do the immobilization. So when the glucose and the enzyme will bind, there will be a chemical reaction that would also need oxygen to happen. So basically, this reaction will lead to hydrogen peroxide, and hydrogen peroxide can be actually electrochemically sensed. So that's basically the byproduct of this reaction that we are trying to measure. So basically, hydrogen peroxide then will go to the electrode side, and then we'll lose some electrodes, and therefore it will basically lead into some current that can be measured by the potentiostat. But we should also note that in body there are all different other kind of materials that could be interfering with our measurements. So namely proteins that are electrochemically active. So in order to prevent these kind of interferences from other chemicals, we need to modify our surface to kind of block these kind of molecules. So for proteins, because they are big molecules, we can use selective membranes like Nafion to prevent them from reaching the electrode. There are also other interfering substances like ascorbic acid, uric acid, or acetaminophen, and these are all abundantly available in the body. So we need to somehow find a way to also block these kind of substances. So in order to do that, we use a layer of polyphenol. So this layer of Nafion is actually permeable for these small substances like ascorbic acid, but then this layer of polyphenol is kind of blocking these kind of interfering chemicals, and therefore we can get an accurate measurement of glucose. Sure. It's a little bit more slides. And you can see here that this cyclic voltammogram shows for different concentration we get different voltagrams. So so as I mentioned, one way of powering the device is to use batteries, but batteries are bulky, so we can use RF kind of powering from outside. Currently available RF powering kind of devices that are used for implantable systems or for retinal implants. They use large coils. They use low frequency in order to minimize tissue loss. But for an implantable glucose monitoring system, we cannot use very large coils and antennas. So we have to find a different maybe frequency band to do that. So in order to find a right frequency band, we need to look deeper into the tissue electromagnetic characteristic. So here, because we are trying to measure subcutaneously, we can look at, we are looking at the skin anatomy. So it's comprised of 3 layers: epidermis, dermis, and hypodermis. And this is the vascular place that we do the measurement from. As you can see, the tissue has a very frequency-dependent electromagnetic characteristic. And as we go to higher frequencies, the loss becomes larger. But at the same time, we know from the electromagnetic theory that in order to be able to have a smaller antenna, we need to push our frequency higher and higher. So there should be basically an optimal frequency band that we could use to power our system that gives us the maximum power transfer. And for example, for the case of 2 loop antennas, we can see that there is actually an optimal frequency band that we can use to power our device. The other constraint here is that there are not many frequency bands available for these kind of applications. So we are almost limited to ISM bands that are around 900 megahertz, 2.4, and 5 gigahertz. So we have actually used this 900 megahertz band to do the RF powering. The other thing to be considered is to communicate, to find a way to communicate between the device and the outside world. So this graph actually shows the standard wireless wireless standards for medical devices. As you can see, the power becomes smaller and smaller as we go to lower and lower frequency data rates. And actually, it's interesting that for biological signal, we do not need very high data rates. So basically, we have actually adopted a passive kind of communication to do the communication between the implant and the outside world. And that's actually in our favor because it's giving us the smallest power consumption, basically. So this is the block diagram of the system. It's comprised of a power management unit that it creates actually a clean voltage to the rest of our circuitry. So we have a receiver that receives the signal from the outside reader, and based on that signal, we'll decide what to do. And then we have a readout circuitry that is connected to an on-chip sensor. It's comprised of potentiostat, analog to digital converter, and last, it has radio transmitter that uses backscattering that I will explain later, that transmits the data from the implant to the outside reader. So the on-chip, so because we are looking into an integrated system, so we have implemented the coil or antenna on-chip using top metal layer. We did extensive electromagnetic simulation using human body model to optimize this design. And as you can see, it has the maximum power gain at around 900 megahertz, which is our band of interest. So we used a simple rectifier, 4-transistor rectifier, which is analogous to a bridge of 4-diode rectifier to do the RF to DC conversion. And because a single stage will not provide us with a high voltage, we have put 3 of them in cascade to create a large enough voltage to be able to drive the rest of the circuitry. And it provides almost 60% of efficiency at nominal load, which is about 6 microwatt. Then the rectifier is followed by a reference generator that creates a clean reference and rejects the ripple on the rectified voltage. And then it's followed by a voltage regulator to create a clean supply to the rest of the circuitry. And as you can see here, by by increasing the transmitted power, we can achieve 1.2 volt at transmitted powers over like 16 to 17 dBm, which is the intended voltage for the rest of the circuitry to operate properly. The signal acquisition part is comprised of a potentiostat, a 3-electrode potentiostat, which has 2 regulation loops. The current signal is converted into a voltage using a low frequency transimpedance amplifier, and then it's connected to dual slope ADC that does the analog to digital conversion and provides a 9-bit word, including the sign bit. So it's actually capable of doing bidirectional current measurements, which makes it suitable for cyclic voltammetry, because in cyclic voltammetry we will be having positive and negative currents. And the performance of the ADC is shown here. It provides a large dynamic range and at the same time nice linearity performance. So this system in total consumes less than 6 microwatt, but because we are very limited in power in the next generation that we just recently submitted for fabrication, we changed the design so that we can reduce the power consumption. Of course, it's not going to be able to do cyclic voltammetry because it's unidirectional measurements. We can only do amperometry, but then this is similar to all other devices that do glucose monitoring. They all use amperometry. So on the receiver side, we use pulse width modulation to send data from the outside to the chip. We use a simple envelope detector to do the signal receiving, and then the envelope detector is followed by a pulse width modulation, pulse width demodulator, and each implant is basically addressed with an 8-bit tag. As soon as the 8-bit tag is received, a trigger signal will be activating the rest of the circuitry in order to make a glucose measurement. So for wireless communication from the chip to the outside, as I mentioned, we are using passive RFID technology. So basically, the way it works is that if you consider a two-coil system with coupling, by changing the load at the secondary side, we are basically changing the effective resistance seen at the primary side. So basically, when we have this coupling system, we can basically change the load at the implant and then be able to detect some changes in the reader. So and basically, this is called in the literature load shifting or backscattering. Backscattering because we are basically changing the matching. We are changing the matching at the secondary side, and therefore there will be some reflection, and we are basically reading the reflection. So that's why it's called also backscattering. So we use the same modulation technique as our downlink system. So we use pulse width modulation, and here we can see some measurement results. So this is the sequence that we are sending from the chip to the outside, and this is what we have been measuring. And also here you can see the clean supply 1.2 volt voltage, and also here you can see the unregulated signal due to this load shifting. We see some wiggles that are rejected by the regulator. So we implemented this system in 0.18 CMOS technology. We implemented the coil using the top thick metal 4.6 micrometer ultra top thick metal, and also the sensor. We did some steps of post fabrication to plate platinum and silver chloride. So usually for the reference electrode they use silver chloride, and platinum was used for the working and the reference electrode and the counter electrodes. Here are some measurement results using chicken tissue. So as you can see here, for about a centimeter distance between the breeder and the CMOS chip, we were able to do powering and also communication. So these spikes show the 8-bit tag that was sent to the CMOS chip, and then these are during this period the signal acquisition happens, and during this period you can see that the signal is backscattered and read from the outside reader. And the reader was implemented using FR4 two-layer PCB board, and we needed to transmit about 22 dBm of power to basically activate the implant. We also did some in vitro measurements this is the glucose measurement using this device. It's in a good agreement with a commercial potentiostat, and we used glucose oxidase to functionalize the electrodes. And this is concentration range is basically a clinically relevant concentration for a diabetic person. We also did some implantation studies. These are just to see the effect of encapsulation. These were done in our collaborators' place in Frankfurt, Sanofi. So we saw that the micro-scale inflammatory encapsulation was formed, but this was small enough so that the diffusion time is not going to be very long. So compared to previous designs, this design actually provides the smallest size, almost more than a factor of 10 to 20 smaller than the other designs, and also it's basically providing a fully integrated solution. So now let me move on to my future research direction. So I've been working on optical interconnects. So silicon photonics is a new research topic that many people are working on. So I will be interested in exploiting this new technology and integrate it with the available CMOS technology to provide higher and higher data rates for the future need of processing system. The silicon photonic technology will provide us with very efficient optical devices with photodiodes with very small parasitic capacitances, modulators, all these devices on the same platform. So it's going to be very helpful for a full solution for both chip-to-chip and maybe at some point on-chip optical communication. Another emerging technology is 3D integration. So scaling has been going on for a long time, and now we are getting to the point that more scaling seems to be becoming harder and harder. So we are using the other dimension. So we have been always going planar. Now we are going to the third dimension. We are stacking up CMOS silicon chips, and it will create its own problems. It will basically give us very high level of integration, increase the speed, and reduce parasitics, but then there will be thermal management problems and things of that sort. So we need to be able to optimize our designs for lower power so that we can tackle with these problems. So the other research area that I'm interested is actually lab in the body. So basically we have done a few iterations of the glucose monitoring device. These are actually the old devices from our group. They were powered with optical signals, but then I propose to use RF powering, and as you can see, the size becomes smaller and smaller, and we are hoping to get to the point that we can basically inject the device using a very tiny needle, very large gauge needle, so that it provides the minimum amount of pain to the user. And also, we would like to also go deeper into body and be able to measure different chemicals like cholesterol, because like people who are suffering, many of the people suffering from diabetes, they also need to be careful about their cholesterol level, lactose, different kind of chemicals in the body. Also, we would like to go even deeper into maybe blood monitoring proteins in the blood using affinity-based kind of detection methods, electrochemically or even optically, to do different kind of proteins that are involved in different kind of disorders. And lastly, I am also interested in reliable neural interfaces to be able to implement brain-machine interfaces, to be able to read neural activities from different parts of the body, from brain, and be able to interpret those kind of signals and help to the neuroscience community. So with that, I would like to thank my advisors at Caltech, Professor Sher, Professor Imami, and some other professors at University of Toronto and Caltech, and also my colleagues at different labs at Caltech. Thank you. Thank you for your attention. Sorry, I went a little bit slow.
It's a very interesting talk. You have obviously a broad range of interests. With the glucose sensor, you have this glucose oxidase, which is participating in this reaction,
Sure.
and it's really being consumed, right? So
Yes.
have you estimated a lifetime for a practical system?
Yes. So there are different mechanisms that will wear out the glucose oxidase. So the first is just thermal. So basically, different substances colliding with the enzyme and degrading it. So that from the factory that manufactures this product is about a year. So that's not a limiting factor. So consumption is the other factor. But we believe that body response will be more severe, and we will be more limited by the body response than the enzyme consumption, basically. And these are all questions that need to be answered because there has not been such a device out there to explore these kind of questions. So basically, we have came up with this device, and next week we are gonna do some rat experiments in Frankfurt, and we are basically hoping to have a good answer for these kind of questions soon. So these are all questions that we also have in mind, and we don't know exactly what would be the limiting factor of the lifetime of this kind of technology.
And does the silver chloride also degrade over time?
That also degrades over time. But from our experience, so we have done some measurements just using blood and serum, and they have been working for even months. So, but that's isolated blood and isolated. It's not in the body. So in the body, everything will be different. So you will be having cells attacking the implant and all these kind of body responses that we do not know about, and we would not know about it until we have this device and implant it. So basically, it's kind of a long process, and we are still in the beginning.
On the on-chip electrical wires that you designed and implemented, you showed that they achieve high teens of gigabits per second bandwidth, and they are in the femtojoule per bit energy efficiency.
Picojoule per bit, yes.
Well, yeah, but 0 point something picojoule.
Yes,
right? So
sure.
In reality, you're in the femtojoule
Sure, in the scale.
regime. So I'm wondering, does this obviate the need for on-chip photonics at this point?
I believe at some point we would need to move to other technologies like photonic, but at this time, copper interconnects can they're actually are good enough for now to answer our problems, but like in the industry they're still using repeaters to do the interconnection. So they're still using a very primitive kind of technology. They have not explored different options using the same technology. So I think for a good while we will be still using copper wires. We only need to be smart and come up with new techniques, maybe circuit techniques to exploit the possibilities of copper wires. But maybe in the long run, we might have to go to photonic interconnects. But you also need to keep in mind that this is kind of a very large change, and industries like semiconductor industry, they are not very willing to go through those kind of changes. And I don't think in very near future we will be seeing photonic interconnects, on-chip photonic interconnects. For chip-to-chip, of course, it's already being used. It's not mainstream, but it will be mainstream soon. But for on-chip, I think there is still a lot to be done with copper interconnects. And there are many technical issues with photonic interconnects on chip. So there is still many, because silicon is not a direct bandgap semiconductor material, so there will be no light emission, so that will be the main problem. Light needs to be coupled to it and then coupled back out for communication. So there are many technical challenges facing photonic interconnects on chip, but theoretically it's much less power hungry than electrical interconnects. But I don't think it's going to happen soon.
So what was that simulation? Was it simple electromagnetic simulation or diffusion optics?
No, we use the HFSS. It's a 3D solver, electromagnetic solver. So there is no optics involved into this simulation. It's just simple Maxwell equations. So this is a 3D solver that just basically solves Maxwell's equation. And we used human body. We used human body model to make accurate simulation, because with and without a human body model it's way different. Body, as I showed here, it's very dispersive. It's a very dispersive medium, and all its characteristics
it's
are.
homogeneous, right?
It's
For that wavelength, it's not matter.
it's not very homogeneous. That's true, but then these kind of models are kind of averaged. Like so, these are all real models that are taken from experiments on different tissues like skin, muscle. So these are kind of an average model. So they basically include that kind of inhomogeneity in them. And also, as you mentioned, in that kind of frequency and wavelength, it shouldn't matter much. And our simulation and experiments were kind of agreeing with each other. So we, from that, we can kind of conclude that the models are pretty good.
All right. Thank you.
Thank you.